In this video, we'll present the proof of the exchange lemma, credited to Steinitz. This is, to some extent, the culmination of the concepts of linear independence and spanning, and it's what tells us that all bases for a given finite-dimensional vector space have the same size. We'll start with a quick review of linear independent sets and spanning sets. Let V be a vector space over some field. A collection of vectors v1 through vn is called linearly independent when every linear relation on the collection is trivial. That is, the only way to build the zero vector as a linear combination of the collection is to assign a scalar of 0 to each vector. Said another way, there exists no non-trivial linear relation on the collection. No combination of these vectors that has a non-zero coefficient for even one of them can give the zero vector. Keep an eye out for linear combinations of linearly dependent sets in the proof. On the flip side, a collection of vectors w1 through wm spans the vector space V. Note this is the verb form of span. It means that for every vector of V, there is some set of scalars that builds V as a linear combination of the collection. You might ask what these concepts have to do with one another. The real answer is that they're the two halves of what it means for a collection to be a basis for the vector space V. But there's a very important relationship between these two concepts that we should prove first. If v1 through vn is a linearly independent collection in V, and w1 through wm spans V, then the number n must be less than or equal to the number m. In other words, the size of any linearly independent collection in V can never exceed that of any spanning collection in V. Note well that the vectors in these two collections need have nothing to do with one another. No matter where they came from, this size relationship must hold. To prove this, we're not actually going to count the elements of either set. We'll just show that there are at least as many elements in the spanning set as in the linearly independent set. This proof is technically one by induction, but the substance of the proof has nothing to do with the technicalities of induction, so we'll simply work through the logic. Follow each step carefully. There are no tricks here, but the result we're after will simply fall into our laps in the end. Before we start, we'll need one previous result for this proof. Given a collection w1 through wm that spans V, and any linear combination of those vectors, if we choose any vector wk of our original collection whose coefficient in that linear combination is not 0, replacing the vector wk with that linear combination gives us another collection that still spans V. This is fairly straightforward to prove from the definition of span. As an example, if we had the linear combination 3w1 plus w3, we could replace either w1 or w3 with this vector and be assured that the new collection still spans V. But replacing any other vector might or might not yield a collection that spans V. Now to begin, we'll start by color-coding our collection so that the logic of this proof is easier to follow. Let's color the vectors of our linearly independent collection red, and those of our spanning collection blue. When we combine these vectors via linear combinations, we'll color the coefficients with that of the vector they scale. Our goal will be to modify our blue collection, one vector at a time, so that it contains every vector of our red collection. If we can do this, there must have been at least as many blue vectors as red vectors and we'll be finished. First, let's try to get v1 into our spanning collection. What do we know? Well, it must be some linear combination of our spanning collection by definition. We'd like to find a non-zero coefficient in this linear combination, so that we can find a vector wk to replace with v1. Now, must such a coefficient exist? Well, suppose not. Then all of the blue coefficients are 0, giving the equation v1 equals the zero vector. This is impossible because it's a non-trivial linear relation on the vectors of our linearly independent collection. You might also remember that a linearly independent collection can't contain the zero vector, and this is why. In other words, there must be at least one of these blue coefficients that is non-zero. And without loss of generality, suppose it's alpha 1. If not, rearrange the blue collection. We can conclude that replacing w1 with v1 yields a collection that still spans V. That's the end of step 1. The remaining steps proceed quite similarly. Let's now consider the vector v2. Again, it must be some linear combination of our spanning collection, which now has v1 in it. We're looking for a blue coefficient that's non-zero. Must such a coefficient exist? Well, suppose not. Then with all the blue coefficients being 0, our equation becomes v2 equals alpha 1 v1. This is a non-trivial linear relation on our linearly independent collection, because if we move everything to the left side, Whatever alpha 1 is, the coefficient of v2 is non-zero. Since this is impossible, we must have at least one blue coefficient that's non-zero. Again, without loss of generality, it's alpha 2. We can thus conclude that replacing w2 with v2 yields a collection that still spans v. Two vectors in. We simply apply this same reasoning to get the red vectors into our spanning collection one at a time. Let's see it one final time to make sure it's clear. Consider the vector v3. It must be some linear combination of our spanning collection by definition. Must there be a non-zero blue coefficient? If not, our equation would become v3 equals alpha 1 v1 plus alpha 2 v2. In other words, v3 minus alpha 1 v1 minus alpha 2 v2 equals 0, which would be a non-trivial linear relation on our linearly independent collection. Impossible. Thus, at least one blue coefficient must be non-zero. And without loss of generality, it's alpha 3, so we can replace w3 with v3 to obtain a new spanning collection. Proceed in this manner until all of the red vectors are listed in our spanning collection. In order for them to fit, there must have been at least as many blue vectors as red ones at the outset, which proves our result. At this point you might be saying, whoa, but how do we know that we don't run out of blue vectors? This is a very natural initial reaction to our proof. In fact, we can't run out, but it's easy to miss the reason why on the first pass. Each time that we need to put a red vector into the spanning set, we find there must exist some blue vector with a non-zero coefficient. In particular, there must exist some blue vector, and that's the key to the proof. This must be the case as long as red vectors remain to be put in, or else we'd obtain a non-trivial linear relation on our linearly independent collection. So we're all good. If you're interested, you're welcome to rewind a bit to see this in action now that you know what to look for. Let's follow up with a quick consequence of this lemma. A basis for V is a finite collection of vectors in V that is both linearly independent and spans V. Now suppose that B and B' are two bases for V. On the one hand, B is linearly independent in V, and B' spans V, so B' must be at least as large as B. On the other hand, B' is linearly independent in V, and B spans V, so B must be at least as large as B'. The immediate conclusion is that these two bases for V must have exactly the same size, which allows us to define the dimension of the vector space V as the size of any basis for V, because they all have the same size. Hope this video has been informative and given you not only an understanding of the exchange lemma, but a little bit of practice with the definitions of linearly independent set and spanning set. Enjoy your future journeys in linear algebra!